let me say a few things. So I'm going to hand the midterm back at the end of the lecture, so someone should tell me when it's like 3:10, so we can have a little bit of time to talk about that. So that'll be at the end of the lecture. Let me talk about, okay, there's a survey that you should fill out. If you have anything to say, you should fill out and make, it's anonymous. Feel free. I don't have responses from all of you. If you don't fill it out, that's fine, but then your voice is not being heard. So if you have anything to say, you should fill it out. So the other thing is the second part of the project. I just wanted to kind of say a few words to clarify what's going on. So the first part of the project was very well defined, and you kind of were given very clear instructions on how to do things, and it was a very constrained project. The second part, and the purpose of the first part was for you to understand how LLVM works. The second part of the project is more of what the real product is, which is actually more of what a grad class project is going to be like. So the idea here is that it's not as constrained as the first part. You have to make decisions, and you have to figure out how to do it. The evaluation is all going to be based on a report. So we're not going to give you benchmarks. We're not going to give you things to run. We're not going to run your thing against a set of, existing C programs. If you want to run it on C programs, believe me, I think you guys are smart enough to figure out where to find some C programs out there, right? If you're okay, then you can also write some C programs, some small benchmarks. Oh, that's nasty. I know, that's like the worst. But sometimes you got to do nasty things, and so that's the way life works. But you can also take some samples. So yeah.
There's something okay if you don't have benchmarks, but there was the issue of which instructions can you actually cover. Because the entire set is huge. They want to define what functions so each possible.
Right.
Kind of out of the scope of what we can do, right? So, what we're asking within our group is what is the set of instructions we should focus on? Right.
So okay. So the way to address this. Okay. You should write a full function that works on every possible instruction. The way you should organize it is that you should basically, by default, return top. And then, that's your default flow function. And then you decide on which statements you want to analyze. And so that way, you're always going to be safe. You should be able to run on anything. And then you could basically then kind of refine it and decide which things you want to do. So for example, if you always return top, you should be able to run your thing on the Linux kernel. I mean, I'm just exaggerating here, but you should run it on hundreds of thousands of lines, and it should be able to work, right? You should be able to reach a fixed point. It should be able to work. So, but the point is that you're not going to learn any information. So then the point is you have to start looking at the reasons why you're not being able to get the information you want to get to perform optimization or to perform the transformations or the things you want to do, and then you can figure out the statements that you want to actually run, that you want to do flow functions on.
So yes, if you return all top, you're saying because you're not giving us benchmarks or goals or anything, you do all top, and then just for a few very small subset, we can say, oh, these kind of things we're going to apply common set of expressions.
Right. So at the end of that's yes, but at the end of the day, so I'm not providing you benchmarks. That doesn't mean you're not going to have. You should come up with a benchmark
and they show that it works for them.
Write your own, or write it. And the point is, in your report, the report is going to summarize. You should have samples of here's how it works on this kind of thing, and here's what it does, and here's the kinds of things that we were able to run it on. And that will give us a sense of what you did. Obviously, if you say here's the CSC, we ran it on 3 lines of code, and that's all we did. We didn't go past that. That's going to be very different than another group that says we ran this thing on 300,000 lines of code, and we actually looked at where it didn't work, and then we actually changed it, and we improved it, etc., and we even showed that it actually improves performance.
I'm
saying that's kind of the
where it stops being intellectual and it just becomes a tedious implementation.
Right.
If we're reaching that point, we're trying to say, okay, that's not going to report.
Well,
it's not.
Right. I mean, I think the thing to keep in mind is that this is a graduate class, so at some level, you know, it's not just about grade, it's about what you want to make out of it, right? So what you want to learn out of it. So this is not, as I said, this is very different from undergrad classes. So I mean, in some sense, the idea is for you to explore new things and try things out and try to see how you can connect the pointer analysis to kind of improve things, et cetera, and to show that, you know, basically the idea is to show that you did something interesting, you did something where you learned something about how to do these things. And you have to basically kind of shine in some way. I mean, obviously, there's a very low, you know, you can do something really, really simple, and that's not going to give you the best grade. If you just do something that runs on very small programs and that's it, that's not going to be as impressive as if you actually go the extra mile of actually, you know, doing some tricky things or showing how it works on bigger benchmarks, et cetera. So does that make sense? I mean, this is basically the bottom line. This is more open-ended. I mean, that's just the way this works. Are you guys surprised it's just open-ended? No, I mean, this is what other black class have projects like this too, right? I mean, it's open-ended. In fact, yeah, I mean, any questions? Any other questions on that? So just to be clear, right, the report is really going to be your main evaluation criteria, so you should actually make the report, I mean, you should basically try to shine in your report and show that this is the goal, is to show that your thing actually does some interesting things and actually you're able to show, you know, explain how it works, show some examples, et cetera, et cetera. So as another example of somewhere you can go the extra mile, you can actually decide to, this is something that's useful, and you can decide to do it, or you can decide not to do it, but it depends on how, but you can actually build libraries that display your information. You can use DOT. Do you know what DOT is? Does someone care to explain what DOT is? DOT. The what? It's a graph visualization tool. So you can basically it's a text, you can describe a graph using a textual description, and then it'll kind of display it to you graphically. So you can, for example, take the control flow graph in LLVM and display graphically, and you also can intersperse your data flow analysis things. And that way it'll kind of create a very nice visualization for you to understand what's going on. You can even use that in your report and describe things about it. So there's many, many different things you can actually do to help you, basically that you can do to help you in this project. Yes?
So what file shall we submit at the end?
Your report.
And?
That's it. Well, actually,
that means there's no way for you guys to check our programs for.
Which is theoretically something that's impossible.
Well, maybe we'll ask you just to submit the code itself. We won't run it, but as a sanity check, just to make sure that you're yeah.
No.
Well, let me yeah, I mean, as I said, this is a grad class. So if you decide to do something stupid, then don't do something stupid. Don't do it. Because it defeats the purpose of everything. So I mean, so if there's something fishy going on, I mean, we can ask you to just show us a demo of your system or something like that. So that's something we can. I reserve the right to still do that. The same way we're going to have a meeting for 10 minutes today on Thursday. I may ask for you guys to just come in for 10 minutes, show me that your system's running or something, just to kind of as a sanity check, just to make sure that you're not like, it's not like all vaporware. It's not like, oh, we did all this stuff and then like actually got it. So okay. So that's about the project. So I put up some readings for next week about pointer analysis. There's 2 readings, and it's just to give you a flavor of what's going on there. I mean, really, you don't need to read the details in paper. Just get a flavor. It's something for you to explore more. I mean, you can, obviously the papers are another example where you can, basically. It depends on how much you want to get out of it. But that's something else. So there's 2 papers. One is on kind of a modern version of Anderson's analysis, which we talked about Anderson, and we'll continue to talk about it. And then the other one is kind of a retrospective, kind of on the issues of pointer analysis. Because pointer analysis has been worked on for decades and decades and decades, and people have been banging their heads across this thing for a really long time. So it's kind of interesting to see a survey paper on this topic. Okay. Oh, yeah, okay, cool. And then we'll do the midterm at the end. So please, someone remind me about returning the midterm. Okay. So you guys remember what this is? What? Really? What is it?
Flow sensitive means it's sensitive to the direction throughout the program that's analyzing it. Flow sensitive is going to be one thing. You just keep going until it's stopped.
So one thing. So basically,
One piece of thing.
one piece of information. So in flow sensitive, we keep a piece of information for every edge in the control flow graph. Whereas when we do flow, and because of that, the order matters, right? So the order of the statement matters, and we kind of have to do this iterative data flow analysis where we reach a fixed point. Flow insensitive, we just run, we basically throw away the order in which the statements are in the program, and we store one graph for one piece of information for the entire program. Okay? And the idea here, just to be clear, this is not just for pointer analysis. This is a general idea. Right, general idea, flow sensitive versus flow insensitive. You can take all your analysis that we've done so far, we can run them in a flow insensitive way as well. Okay? All you do is you take your flow functions and you run them, you keep on running them, and you basically keep on adding information. Sometimes what you do is you're never allowed to delete information. Okay? So what happens is you run the flow function, and once you get the result, you take the previous result and you take the new result and you have to join them. Right, you have to basically, it's almost like you have you assume that the two are either they came from a merge, right? They're both of them have to hold. And then you can kind of do that in that way. And you can do that for any kind of analysis we've done so far. You can run it in a flow insensitive way. And the benefit is you only store one piece of information for the entire program. Okay, for the entire program. Okay, what was this called? So this was just our flow sensitive normal analysis. And by the way, this is the one that I would actually recommend you try doing in your program analysis. Just try doing this one, the kind of the flow sensitive one in your project. And that'll be what?
Isn't it required?
Yeah.
You said you need it for every instruction.
Right, so that's the one that I want you guys to do. I mean, I don't want you to, don't do Anderson or the more advanced one. Just do the kind of simple one, the one that you did on your midterm as well. So actually, it's interesting because you'll see how this actually pans out in practice, what kinds of things what's the extra mile you have to do to get it towards the project. So, and the benefit here is that, benefit is only one piece of information. Drawback is, what's the drawback? Less precise. So basically, it's this is kind of the way thing where it says you can't figure out the ordering of these statements anymore. So you have the statement x equals y, x equals z, and in here, you basically will your flow intensive analysis will figure out that x may point to z here, which is totally wrong. Well, not wrong. It's imprecise. Your flow sensitive analysis will figure out that here x will only point to y. Okay. Okay, let's try. So why don't you guys try to do Anderson on this thing? So Anderson is let me just clarify. Anderson is this analysis that we just saw where it's flow insensitive, and you have to keep on iterating until you don't add any more information. Right? That's the way the Anderson works. So why don't you guys, and we still have, by the way, the summary nodes. These summary nodes are, if you remember correctly, these are nodes that represent an unbounded number of things at runtime. So that's that. So why don't you guys try to see what this looks like, and then we can do it together on the board. Just give it a quick try, just to get a feel for what these things look like. Because actually, it's a little bit tricky once you actually start doing it. There's a lot of self loops, a lot of weird things that can happen. It's actually, it can get kind of confusing.
Can you switch back for just a second so I can look at the other one?
This?
To the other one. Yeah, that one. Okay.
sensitive or insensitive?
What?
So should we do sensitive or insensitive?
Flow insensitive.
Okay.
So the order doesn't matter. Just keep, just keep on, okay. So let's try to give it a try. Let's see if we can figure this out. So even if you're not done, let's try to figure this out. So, by the way, one of the things that you'll notice is that once to figure out which statements you may need to run again, you basically can see what things get modified, right? So it's the thing that like, for example, if Q points to something new, then basically you have to reanalyze the statements like these that involve Q, right? Because if Q points to something new, then these statements, if you rerun them, it'll possibly give you more stuff. So if you run the first two statements, this is what you get. P points to S1, Q points to S2. Then we do star P gets Q. So basically, star P is S1. So S1 now is going to get the value of Q. So Q points to S2, so what this means is that S1 can point to S2, right? This is very important to make sure you gotta get, this is what's going on, right? Star P is S1, and S1 now will point to whatever Q, you're taking this Q value and storing it here, so since Q points to S2, S1 can point to S2. Okay, this one's easy, R points to Q. Okay, now what? Star Q, which one do you guys want to do? Star Q is this one? Star Q gives R. So S2 points to whatever R points to. So star Q is S2, and S2 points to whatever R points to. So what does R point to?
Q.
So S2 points to Q. What about S equal to R? So, well, this S is going to point to whatever, right? That's, right? Okay, what about the other side? Star Q gets P. Whoa, wait, what? Star Q is S2? So star Q is S2, and S2 points to whatever Q points to, so S2 goes S1. Okay, cool. And now S is equal to P. What? Oh, wait a minute. Wait, so what does S point to now? And then this star R equal to S. So what's star R? So star R is Q, and this is equal to S. So what is the thing that S points to? S1 and Q, so Q should point to itself in S1. Okay, what next? Are we done? Start over. So so we start P. So okay, we run this one. Does this change anything? Oh, because Q got modified, right? So the thing at P. So S1 now needs to point to whatever Q points to, and Q points to S2, but now it also points to S1. So S1 points to itself, right? What? Oh yeah. Oh boy. See, so it's actually pretty tricky. So wait, so S1 now points to Q? Right, because Q points to three things. There's three outgoing edges of Q. S2, Q, and S1. And so now S1 will point to those three things. S2, Q, and S1. Okay, this is going to be remain the same. What about this? Star Q equals R. Whoa. What? Are you sure?
Everything they like for that one, everything Q points to. Right?
So star Q is S1, right?
It's anything that Q points to has to now point to.
And what does R point to? Oh, I see. So S1 just points to. Okay, fine. So that's not. What about this one? Star Q equals P. So now P. Oh, and we already have. So start P. Huh?
Everything Q points to already points to S1.
Simple about it, so like putting all equality but in the same box. You call them like the same box, so like circle back and put them back. Like when you say like argue that, just treat them.
Sure. I mean, these things, but they're actually, this is the only thing they're equal. Sure. Well, actually, they're not equal. Yeah, actually, they're not equal. Because R points to only Q, S points to Q and S1. You could merge them.
But at any point you can execute that equals R law, right? You repeat it.
Oh, you're basically saying, you know what,
You can just read the executed.
no, but no. No. Hold on. Because I think you're jumping the gun because we're actually going to talk about this in a second, but so if you actually have, this assignment here, right? That doesn't guarantee that S and R are the same, right? Oh, no, right? This is a little bit confusing. Because, so you might think, oh, this assignment means that S and R are the same. No, because S is also, basically actually what this means is that anything that R points to, S will also point to that. But the thing is that if you only had that one assignment in the program, yes, S and R will always be equal. But you have this other assignment. And what this assignment says that anything that P points to, S will also point to. But basically what you have is that S is just going to have everything that R points to and everything that P points to. Right? So S is going to have more than what R points to because this other assignment is also kind of adding stuff to what S points to. Right? And actually you can see that here, which is that basically R and S are not the same. And even if you execute this assignment, S equal to R, if you do this S equal to R, what's going to happen is R is still just going to point to Q. In fact, R will always just point to Q, I think, in this example. Where in fact, S will actually point to many different things. Does that make sense? So in fact, they're actually not equal. Okay, but that's a good question because we'll see later on that there are actually, that really what's happening here is that this assignment is being run in a particular direction. There's a directionality included here. And what this means is that if you have these two assignments, what this does is everything that R points to, it makes S point to that. So basically the set of things that R points to must be a subset of the thing that S points to in our flow incentive solution. And the set of things that P points to must be a subset of what S points to. But S will have both what R points to and what P points to. And we'll see later on that we will actually change that to basically do exactly what you described, just to make everything equal. But we'll get to that in a second. So hold on, where were we? Wait a minute. No, we're not. What?
We are at start Q.
Are we finished? But now so you think we're done, but we just need to make sure we're done. Okay.
We just did the article address.
I just did this thing. Okay, so star Q equals R. So star Q is basically, star Q is S1 and S2, right? There's two things. And what's R? R just points here. So it's just Q.
Q also points.
So basically S2 and S1 should point to Q, but they already do. Huh?
And Q.
Oh, and Q, yeah. What about this one? Star Q, oh, wait a minute, is equal to P. Oh yeah, so this one, star Q is S1 or S2. And so now S1 and S2 have both have to point to S1, which they already do. The S equal R, that's already set up here. The S equal P, that's already done there because basically P points to S1 and S points to S1 already. And star R equals S. Star, wait, are we really done? Wow, it's amazing. Wait, star R. Yeah. So star R is Q, and S points to Q and S1, so basically Q has to point to Q and S1 and already does. There you go. It's a little bit confusing, but the point is that, I mean, so that's how this works. Okay, now, did everybody get the point about S, R, and SP? I mean, the S and R are not equal, and S and P are not equal, because we have these two assignments, and the assignments are directional. And we consider that both R and P in some sense flow into S. All the stuff that's in R and P goes into S, but not the other way around. right? Whenever R points to something new, S has to point at something new. Whenever P points to something new, S has to point at something new. But whenever S points to something new because we got it through P, we don't make now R point to that. Right? We're only making the constraints go in one direction. Yeah.
What if we have consecutive statements, like outside of the branch, like if we had at the bottom of the loop, instead of just looping back to the top, if we had S equals to 1 and then S.
We have what? We had what?
If we just had at the bottom of the loop there, if we have S equals to R, and then after that S equals to T, do we do the same thing? Do we just like add arrows as if both are true, or do we?
So, okay. So first, since this is a flow sensitive analysis, it does not matter where you put the statements. So you saying, oh, if I add a statement here, it doesn't matter if you add it here or there or anywhere. It's all the same. Now, if you add another statement S equal R or S equal P, duplicate statements don't matter either because now it's just a bag of statements. We're not really considering the order. So adding another statement, so for example, if this statement appears 20 times in the program, it's as if it appeared just once.
My question is basically, we never delete arrows, right? We always add them.
No, in this, so because, yeah, in this case, we never delete arrows because whenever we have an assignment, let's say, you know, X equals something, previously, if we had X pointing to a whole bunch of things, we would delete all these things and make X point to Y. But that would only hold true right after this statement. But here we're capturing only one piece of information for the entire program, so that piece of information must capture not just what happened after the statement, but also what happened before the statement. And so we can't delete that information before the statement. You have to keep those 3 arrows. So, yeah. Now,
Is there ever a case with flowing sensitive analysis where you want some kind of must point to scenario? Or is it always?
no, it's really hard. That's really, really hard. I mean,
Or is it always be a may point to?
yeah, I mean, it's very, very hard to get those kind of strong updates. Now, if you look at a flow-sensitive analysis, you can do strong updates. In other words, when you have, when you have something like this, you can basically make it point to something, to delete this thing and make it point to something else. But you have to be careful about things where you have summary nodes. So you should be careful. For summary nodes, you should never, ever, ever delete information because these summary nodes basically represent a whole bunch of information, right? It's many, many different possible things. So for example, if you have this points to a summary node like this, which points to somewhere, and then you have this statement, star x equals address of y, and this is, let's say, z or something like that. You can't say, oh, well, star x points to just one thing, right? X points to only one thing, and then, oh, well, I'm updating this s1, therefore, delete this and make this point to y. That doesn't work because that x1 represents not one memory location. If that x1 were just a variable, you could do this kind of thing where you say, well, x points to only one thing, therefore I know that this star x really will make that thing point to y, so I can delete that edge, make it go the other way. So I'm just telling you this for your implementation when you actually implement things. But when you have a summary node like that, you cannot delete the previous information, even in a flow-sensitive analysis, right? I mean, you can't delete this because this summary node represents many, many, many memories at runtime. It's a huge kind of span of memory locations, and you just don't know which one of those you're modifying. So in fact, the point is, this is not must point to information, even though it points to one thing, because this X may point to any one of the things that are in the S1 summary. Okay. Any questions on that? Yes.
If we take this flow sensitive analysis and if we eliminate all nodes or any edges which, if there's any variable from which there are like multiple edges that are arising out of that, if we eliminate all those and if we retain only, let's say, like, P goes to S1 because there's only one, then like would that subset give us like something close to like a mass quantum analysis?
Yeah, I mean, you're basically saying, you basically ignore all the S1.
Ignore all ambiguity.
all ambiguity, yeah, so there probably is some way to get some must point to analysis, but you have to be careful how you do it. I mean, yeah, I mean, if you reach a fixed, certainly once you reach a fixed point, if there's a variable that points to only, and you include null also. You also have to include null in your analysis, so if something is null, it should point to null. Then in that case, you're right that and you have an X that's not a summary node, and it points to only one thing, then that thing really, you're pointing just to that one thing. But, yeah. But you have to be a little bit, yeah, you have to be really careful. See, here's the problem, though. The problem is, what if, okay, it's flow-sensitive information is very, very weird, because, so suppose you have, I mean, the issue is, you have to also assume that your variables are never used. So, okay, let me put it this way. So, you have the statement X equals X to Y, okay? So now you're saying X must point to Y, right? It's like, I know for sure it's going to point to Y. Okay,
Not the case.
but what about right here?
It's going to.
Yeah, it's like, it has to, but what about, right, so in a flow-sensitive thing, it's really because you may actually be asking information about that variable when it maybe hasn't even been initialized. Now, you could argue that maybe your analysis is set up in such a way that whenever you're going to query the points to analysis results, you're never going to query it in a setting where that thing hasn't been initialized. But of course, all these things matter in terms of the interpretation. So it actually, yeah, so. Okay, so now, what's the next step? I'm going to erase this. So, wait, is that right? Okay, well, you guys can check if it's right. It looks like this. Okay, so the worst case complexity, so Anderson is actually, when you actually look at the details, the worst case complexity is relatively bad. Because, you know, if you have X pointing to a whole bunch of things and Y pointing to a whole bunch of things, if you do star X equals Y, basically you're going to have to go through all the things that X points to and add edges between all of these things. And so in a program, this could be on the order of the number of variables in the program, right? I mean, basically, let's say these are half the variables, these are half the variables, so it's like n over 2 and n over 2, where n is the number of variables in your program. And the number of variables in your program can be proportional to the size of the program itself. So that's why, so this step here is in some sense just one step in Anderson. Worst case is n squared, where n is essentially the number of variables, and which could be proportional to the size of the program. So in the worst case, it's n squared in the size of the program for just one step of Anderson. But then you got to run Anderson at least once for all the statements, right? In fact, probably more than that to reach a fixed point, but at least once for all the statements. So you're going to get at least an n cube algorithm. Does that make sense? You guys see? Okay, n cube is really, really hard to make it run on really large programs. Now, there is a paper that you guys can look at that actually there's clever ways of encoding data structures and doing all kinds of things where you do all kinds of what are called cycle eliminations, where you actually figure out that certain things are going to be equal, and you collapse them into a single node, and there's all kinds of things you could do to make it faster. But fundamentally, a naive version of this is just not going to scale. And even if you implement better versions of this, if you want to run on like a really large program, like 10 million lines of code, this is just not going to scale, even with improvements in the state of the art. So okay, so this is a new idea here, which is actually what people came up in the mid-90s, and so the idea here is that so the problem with this thing is that you have this kind of really nasty kind of cross product here, that everything here basically does this crazy cross product. So what you could do is you could say, you know what? Instead of having X point to a whole bunch of things, we'll always have the invariant that X points to only one thing. And what we'll do is we'll collapse whatever X points to into just one node. Now, this should not be totally unfamiliar to you guys because we already have these notions of summary nodes. So these are just going to be, this is going to be a summary node that represents the variables A, B, C together, right? It's like a node that represents all those three locations. And this will be a variable that represents D, E, F. And when you have a statement like star x equals y, now what you do is you have this, right? It's just one edge. You just add one edge because x only points to one thing. You go, you look at that, and then you just add the edge to whatever y points to. Does this make sense? No? So okay, the idea that we're going to have is we are going to collapse our points to graph so that every node only points to one thing. So whenever in a points to graph you point to multiple things, you just take those things that you point to and you collapse them into one node, and you create a summary node that says this is the set of, it's one node that represents the set of things that this x points to. So in our example, instead of having x pointing to A, B, and C, we collapse these three nodes into one node, a summary node that represents the locations A, B, and C together, right? It's just something that represents all of those locations together. It's only one node in our points to graph. How do we update them? So we'll see in a second how you actually do it. But the way you update them is, I mean, it's similar to the way we updated the summary nodes like S1 and S2 before. Those were nodes that represented many different things at it represented more than one, just one memory location. And so the way you update it, for example, if you have this statement, star x equals y, then what does x point to? It points to this node. And what does y point to? It points to this node. So basically, all this thing does is it just adds this arrow. Right? But now, of course, this arrow is a weird arrow. It really says that basically either one of these ABCs points to either one of these DEFs. Right? And we've lost kind of completely any kind of precision about this. We just, yeah. So let's take a look at how this actually works. So, oops. So what's the more general case? So the more general case is like this. So we have, how do we maintain this invariant? That's one of the questions that we got, because it's like, it's great to say everything points to just one thing, but how do you maintain that? Well, say you have x, and it points to a whole sequence of things, and notice how it has to be this way. It cannot point, x points to only one thing, and this thing points to only one thing, right? So it has to be this linear chain. And y has to be this linear chain too. And when you use star x equals y, what would be the normal, what would you normally do? If you just did the normal Anderson analysis, you would have, what's star x? Star x is this, and this would point here, right? That's what you would normally do. And this violates our constraint. What was the constraint? We wanted every node to point to only one other node. So where's the violation? Right, this points to here, and it points to here. So what do we do to fix that violation? Collapse. So what we do is we collapse. Whenever you have something that points to two things, you just collapse what that points to. So here we collapse these two into basically one node, and then now what happens? Oh, so now we have this big node points to two things. So now we have to collapse these. And we just keep on doing that. And in the end, what you'll get is something like this.
So this can be cyclical then?
What?
I guess we always could.
Yeah, we always could be cyclical, sure. Well, so...
Like that bottom right there on the Y chain might have been X.
Yeah, so cycles are weird. Well, yeah, you have to be careful. So cycles are weird because cycles are very, they're kind of like, it's like a blob that takes over. Yeah. Right? Actually, this is actually a well-known thing that happens when you do these kinds of analyses. You get this big blob because what happens is with cycles, you got to be really careful, right? So let's say you have a node that points to itself.
Why did you self-cycle as much as, like, if the bottom of that Y chain was X, you'd end up having...
Oh, you mean if this thing pointed there?
Yeah. I guess it doesn't actually change anything.
Yeah, I mean, yeah. But But be careful, right, so it's interesting, what happens if you have, for example, a cycle like this? This is fine, right? But what happens if this points to something else? Huh? Yeah, so this is not okay. This node points to two different things. So in some sense, this actually will blobber up and will eat up this node, right? Because this now will have to kind of be merged. So basically, whatever this node points to, it points to this and this. Those two things need to be merged. So it'll merge these two nodes. And so that's why when you start getting a cycle, that cycle will just eat up everything. Like, that cycle will just eat up anything that it starts pointing to, it'll just like eat it up. And that's why you actually, in this kind of analysis, you actually end up getting a huge, huge blob that's so totally imprecise. With one cycle, going to itself, it means that any one of these things can point to any one of these other things, right? So it's very, very imprecise. But let's take a look at what happens in other statements. So, okay, what about this? So what would we do normally here? So again, the theme is we do whatever we would do normally with Anderson, and then we take a look if any of our invariants have been violated. And if our invariant has been violated, we have a node pointing to two different things. We then start collapsing things. So x equals star y. Whoa. So where's star y? Star y is here. And now x will point to whatever star y points to. Right? So it's going to be like this. And now x points to two different things. And those two things that are being pointed to by x need to be collapsed. And then this node now points to two things, so these need to be collapsed, et cetera, et cetera. It's going to collapse, and what you get is this. Yeah?
I think I'm not absolutely over here. So the arrow, does that represent where x points to, or does
Yeah.
that represent some kind of state?
That just represents where x points to.
So does that mean that what it points to is also a pointer? What does the change arrow actually mean?
Yeah.
So okay, so if the value in a box is another variable.
But that variable maybe points to something else too, right?
And if it was just
So for example, I can do t equals address of y, and then star x equals t, then this star x, whatever star x points to, will point to y, right? So you think you could do, right? So whatever star x points to is also a pointer because it points to y. So you can have these chains. In fact, that's what usually happens. That's what usually happens in a points graph, is that you get things that point, especially when you get fields and stuff like that in object hierarchies, things point. You keep on having nested pointers.
so the end of this chain is just a variable. It's not a pointer.
The end of this chain, yeah. Well, the end of this chain, yeah, or a constant, yeah. Well, the end of this chain is actually something that doesn't point to anything else, which is probably about something that contains like an integer or a value that's not a pointer, right? So it'll end with something that's not a pointer, like 5.
Okay, I just asked that because first when you said x points to y, why did you draw the arrow from the second element in the chain to the second element in the y chain and not just y itself?
Wait, because this is x equals star y, it's not x equal to y. You mean here?
Yeah.
So star x equal to y. So what is star x? Star x represents this variable.
Sure, but
And I'm assigning this thing the value of y.
yeah. So what's the arrow going to the thing that like?
Because it's not star x equal address of y. If you have star x equal address of y, this will point to y.
Okay.
Right? If star x equals y, so whatever y points to, this will point to as well. Right? So that's a very important distinction. This is not star x equal if you have star x equal address of y, you would then have this point there, and then you have to merge this and that, because whenever this points to two different things.
So x and y both point this way.
What?
X and y are both pointers.
Yes. In this case, yes.
So
What?
we're just looking at it from the perspective.
Okay. Well, sure. So let me just say the way you can figure out this pointer is this is the points to graph. So this says that y points to something. So that's how you would tell. Yeah.
And
in general will just add the new edge. And
In general, just Ren Anderson and then collapse things. That's how you would think about it. So that's how you would think about it. That's how you can think about this analysis. But when you implement it, actually you do it differently. But wait, we do this. What about this? So x equals y. So what happens here is x gets the value of y, right? Like that.
Yeah.
And then we basically merge everything all the way down. So it'll basically create something where x and y both point to this merged kind of thing. What about y equals x?
Y will point to y. And what difference is there?
Huh?
The arrow goes the other way, unless you mean doing that after the first one.
Yeah, but it'll be the same, it'll look the same.
Huh?
Do you mean like, what if that was the next instruction?
No, what if you ran that instead of x equal y?
Just have the arrow go from y to,
Okay, and
that
then,
wouldn't change.
yeah, you'd have the same graph. I mean, in the end, you'd merge the exact same node, then x, basically what happens is you're merging these two, and then x and y both point to that thing. So actually notice how x equals y and y equal x do exactly the same thing. And what it means is that when you do x equal y, you lose the directionality. Remember before we had this thing where we didn't lose the directionality. When we did x equal y, we had that whatever y pointed to, x pointed to, but you didn't have the contamination the other way around. That if x pointed to something, it wouldn't necessarily force y to point to those things. And you can have, for example, previously you can have another assignment, x equals a, and now x would point to whatever a points to, and x would point to whatever y points to, but the a and the y wouldn't get contaminated. Here, what happens is, this actually is totally, it's symmetric. Now, after this assignment, the directionality doesn't matter. Basically, now x and y will just point to the same thing, and it'll just, they will always point to the same thing. Whatever, if you ever get any information about y, it'll go to x, and whatever information about x will go to y. Yeah. So the reason why we're doing all of this is because once you do this, it becomes almost linear time. And the reason why that is basically this thing right here. I mean, you can see how the worst case, this worst case, has now been completely obliterated. Before we had that every time you did one of these things, you could possibly do this n squared kind of cross product thing. But now this worst case scenario doesn't happen anymore. Because x can only point to one thing. You just go and look up what it points to and add this arrow, and that's it. And then you have to kind of merge things, but that's actually relatively kind of straightforward. And there's ways, there's efficient data structures for actually doing this using. Oh yeah. Oh my gosh, you lose a lot. But at least you run. On your program. And that's the trade-off. The point is, if you have 20 million lines of code, like n cubed just doesn't work. I mean, you can just do the math. I mean, it just really doesn't work. And so you actually have to get to a point where you can actually even run on the program.
Just n, right?
What?
So this will just go to n, n.
More or less, it's almost n. It turns out that it's actually you're using to do this. You actually use union find data structures to keep these unions, to keep these sets. And it turns out that you're almost linear. It's like there's an acronym function in there, but it's basically almost linear. And this stuff is the only thing that really scales for sure. Now, there are ways of regaining precision where you do this to get like information for everything, and then you can basically add more local information. Let's say you do an intra-procedural flow-sensitive analysis, and you kind of you get more information about it. The places where you don't know, like at a function call, or you get after function call, you just don't know what happens. Then you can just go back to this information. But yeah, I mean, the key thing here is to get it to actually run on large programs, and that's what we're doing all this stuff. So okay, we get that. This is basically x equals x to y. I mean, basically x now points to y, and then you merge these things, etc. So okay. So this thing is actually called. So just to say, this thing is actually called Steengaard's analysis. This was actually developed in 1995. There's kind of two really famous analyses. in point analysis is Anderson and Steensgaard. These are like the staples. Like, it's just like, literally like, it's just Anderson and Steensgaard are kind of the main analyses. Steensgaard, the way that it was formalized, you actually look at the 95 paper, it was actually formalized as a way of kind of, the way it was basically said, oh, let's look at point analysis from the point of view of type checking and use types to encode what things point to. And because in a program, a variable like X can only have one type, right? It can only have one type in the program, then it's essentially the same thing as saying it can only point to one thing, okay? So in that paper, it's all based on these types and all this stuff, but at the end of the day, really that's the constraint, that every variable can only point to one thing. And in the original paper, it was basically based on saying that the variable has only one type, but here we're kind of doing it more in terms of these points to graphs.
So why does he give credit for this?
Because he invented it.
But unknowingly. He uncleverly.
Oh, no, he didn't know. He actually came up with this idea of the types, and he showed that this is near linear. Yeah.
Oh, and generalized it to do this.
Yeah, I mean, well, no, I mean, what he did is that, he basically said, let's look at points to analysis from the point of view, like, points to analysis doesn't scale. So what we'll do is we'll do this type-based approach, where basically every variable has a type, and the way it works when you do, in simple languages, when you do x equals y, that forces x and y to have the same type, right, unless you have subtyping. But basically, if you ignore subtyping, right, if you do x equals y language, then x and y have to have the same type, and that forces basically the two, because Keezer was encoding points analysis in the type system, that forced x and y to point to the same, to just one thing and the same thing. So yeah. But if you read that paper, it's actually really confusing. Because it's all in this type framework, and all, whereas in fact the idea is really, really simple. It's that you only have one thing that you're going to point to, and that makes it very, very efficient. Okay. So the other thing that's actually neat about this is that you can actually go and you basically, okay, this is what's cool. You can actually do Steensgaard in one pass of the program. Okay? So the reason why we had to iterate before, if you remember, was that before we had things like x pointing to one thing, and then we had a star x, and then x pointed to something else. Right, while we were doing, we found out, oh wait, x points to something else. We need to rerun the star x statement because now x points to multiple things. The point now is that x points to only one thing, so there isn't this thing where all of a sudden, oh, it's a point to this other thing. And if you ever get to star x, and x doesn't point to anything yet, then you could basically create the node that it points to. You create a dummy node, and that will serve as the thing that x points to, and eventually it will get merged. If x points to other things, it will get merged into this thing. So basically, by going through one pass of the program, you can get the results. You don't actually have to iterate. So this is another huge benefit of Steensgaard. So literally, you take a program, you process every statement once, and that's it. You're done. Okay? So it's actually really, really cool. Very imprecise, but really cool. So how do we do this? So, okay, L points to, so this is our same example, which we did first in a flow, and by the way, Steensgaard is like totally flow insensitive, right? It's flow insensitive, and it's also, not only is flow insensitive, but it also doesn't, so flow insensitive, it doesn't distinguish the order of statements, and it doesn't even distinguish the order in which the assignments are being made. Right, so if you do P equals L, it's the same as L equals P. So it's even less precise than Anderson in that way. So okay, so how does this work? So L points to S1. Now what happens?
P points
P points
to the same thing.
and it points
So
back.
now P, wait, what? No.
No.
The invariant is everything has to point to one thing. So what the only constant is when you have one node having multiple outgoing edges. So here there's still one edge coming out of P, one edge coming out of L. Okay, T equals mu comes.
Okay.
So T points to S2. Star P, okay, star P gets T.
Star P. T.
Right? Is that right?
Yeah.
Okay. What? Is it good?
You did super note. That's fine too.
Wait, what? Not yet. Do I?
You're not, that 2 gets pointed to S2.
No.
Pointed from, pointed from.
Okay, the invariant is, the invariant is, you look at it exactly, so it's, you allow one node to be pointed to by multiple things. It's just you allow nodes to have multiple incoming nodes, incoming edges, just the outgoing edges that you want to look at. So now, now something's going to happen. So P equals T. So P now points to T. So P gets T means that P also points to S2. But now P and S, you have this thing, so that will actually collapse as S1 and S2. So in fact, what happens now?
This one is here.
What about the equation that S1 points to?
Yeah, exactly. So we have to be careful now. So when we collapse these two nodes, we actually have to add a self-edge in that node because it's possible for S1, right? I mean, when we collapse these two, we have to make sure that we add a self-edge. Yeah, absolutely.
Oh, okay.
And that's it. Okay, so we're done. This is it. One pass in the program. It's pretty cool, actually.
So it looks like S1 may point to itself in this one.
Yeah. So it's imprecise.
So you need to erase one of those P arrows.
Oh, yeah, sorry. Well, this P just points to P. Sorry, P just points to this. So basically, let me just show you the difference. So this was a float sensitive, and it was subset based. Subset based in the sense that when we did the assignment, it actually kept this subset relation. Then we had the flow insensitive, still subset based at Anderson. And then this thing is called flow insensitive, but it's unification based. In the sense that when you have two things that point, a node that points to two different things, you take the two things that it points to and you kind of unify them. Okay? And in other words, the reason why it's called also unification is because when you have an assignment like this, P and L are basically, in some sense, the things that P and L point to are kind of unified. Okay? So, yes, you're right. This is less precise. We now have only one summary node that represents everything that's allocated in this program ever. We don't distinguish between things that are allocated at X1 and at X2. So here, we were able to still figure out that, for example, T and L never point to the same thing. Right? Here, we were able to figure out that T points to this S2 and L points to, so these nodes represent distinct memory locations that are different, right? These are the things that are allocated at X1, these are the things that are allocated at X2. So T and L are different. Here we can't even figure that out. Okay? So you're absolutely right. So we lose precision. There's no two ways about it. I mean, and that's the trade-off. The trade-off is when you want to start running on larger and larger programs, to get scalability, one of the big ways you get scalability is you have to give up on precision. Okay? If you want to run on large programs, you have to give up on some precision. There's just no two ways about it. Okay. So, any questions on this? Yes?
Yeah, when we check the number of outgoing edges, we also consider self-reach, right?
Yeah.
Which means if you do one merge, it might cause a lot of...
Oh yeah, exactly. That's absolutely. And you also get this phenomenon of the blob, because basically you get this blob. So now basically what happens is, I mean, anything that this blob now points to, if you ever get something, like let's say you say star L equals, so let's say you do this, right? You have a statement in your program that says star L equals address of X, let's say. Right? So then X will just be blobbed into here. Right? Because star L will make this thing point to X. But now because this thing points to X into itself, it will kind of eat X up. Right? X will just kind of be, it's almost like I don't know. Blob. Yeah, blob.
Almost.
It's like in that Terminator movie where it's like just the blob of the metallic thing that just keeps on like adding stuff to it, right? So I mean, essentially, as soon as you have this, and actually this is a phenomenon that actually happens, which is that basically the heap ends up being a lot of times a big blob of stuff, a huge node that represents most of your dynamic allocation, and it points itself.
So can S1 and S2 still be like separable and other, if you need them elsewhere, or is it?
Well, in SteamGuard, you mean, or?
Yeah,
Well, I mean, so by default, no, but you can basically combine it with another analysis. I mean, if you can basically rerun your thing, you can run a local analysis that gives you more information, or you can do all kinds of other things to recover some information, some local information. For example, I mean, you can, so inside here, you can still kind of figure out that, look, at this point, I know L is points to S1, right? I mean, it would be kind of silly to, yeah, I mean, at this point, I know L points to just S1. Why would I why would I not? So there is a way where you can say, you know what, for this kind of local stuff, I can kind of recover some local information. But whenever you get the function call, for example, if you call a function foo, then after that function foo is called, then what do you know? Then it's very hard to know anything, because maybe if L, T, and all these variables are global, then they might have all been modified in that function. So what do you know? Well, then you have to go back to the SteamGuard information. And so what SteamGuard gives you, it gives you basically a piece of information that you can get for the entire program that's safe. And you know it's safe, and you can fall back on it if you ever get in trouble with not knowing what you're supposed to do in terms of pointer analysis. Yeah. So another way to think about it is that when you use SteamGuard, this SteamGuard analysis on the entire program can now become the top of a more precise analysis, right? Where basically you have a more precise analysis, and whenever that analysis gives up, instead of just literally going to the top of the pointer guard, which is everything points to everything, you know, it can go to the SteamGuard thing. Yeah. What? No, it's not.
You wanted 10 minutes?
There's one more minute.
one more minute.
I have one more minute.
I apologize.
Oh, and I'm talking 3:08. Oh, 3:09. I have one more minute. Hold on. Okay, fine.
Unless you're at the end of the slide, I didn't want you to get.
So actually, the rest of the thing is just some more examples, which we can do together next time. But that kind of more, so basically, that kind of conceptually covers the material that I wanted to cover for point analysis. Next time we'll just finish up these examples. And also there's 2 papers for next week to read on point analysis. That'll give you more background on it. So the midterm, okay, so let's talk about the midterm for just a second. So it's out of 45, and the average was 35 out of 45. And you can, I mean, you know, I'll return it. The thing is, one thing that I usually do is that, I mean, so what happened is that it's a very wide distribution. I mean, there's actually a non-trivial number of perfect scores, but there are also some relatively low scores. And so what I'm going to do is, there's a final too, and the final is take home. And it's going to be a lot longer and harder too. It's going to be more open-ended. But the point is that if you actually get a better grade on the final than on the midterm, percentage-wise, then I can take your final grade and make it count on your midterm grade. For example, if you had a really bad grade in the midterm, that way you could still redeem yourself in the finals, right? This is the intent of this.
Then you'll chunk the entire midterm, so it won't count.
Sure. That's one way to think about it.
Whatever's best for it.
Right, so basically, well, I mean, or the other way to think about it is that if you got like 50% on your midterm, and you got like 75% on your final, then I'm going to just upgrade your midterm grade to be 75%.
Right. If you do better on your final, it counts as your midterm.
Exactly. But not, huh?
Yeah.
What?
It was the other way around.
No, it does not work the other way around, because the final is up, because the final covers more. So I mean, the other way around would be too much, because if you did well here, it doesn't mean that, I mean, there's a lot more things to recover in the final.
We have to.
You don't have to take the final.
I think if you did well in the midterm.
Yeah, then you don't have to take the final. But you don't have to take the final if you don't want to. I don't have to grade it then either. I mean, if you don't take it, I won't grade it. But then you'll get 0.
And then you'll be able to stop.
Yeah, exactly. So, okay, so yeah, so you can get they're alphabetically ordered here. So it's actually, let me spread them out. Let me just spread these out here, and you can come and get them. And then also, we're having our meetings today for the project. So for those of you that I'm meeting with, we're meeting at 3:30. So, wait, did everybody sign up for a meeting? If you haven't signed up, you should definitely sign up ASAP.